Hi everyone, welcome to the Mango Experience, and today we're here to unravel the science of gluten. This is a much contested protein. We really want to know what is its molecular structure, what function does it play, and how do you use it in the kitchen. So let's dive in. Gluten is a protein molecule that is found in a lot of the flour that we use in the kitchen. It's responsible for elasticity and holding the shape of the protein. At the molecular level, gluten is made up of two key proteins, that is glutenin and gliadin. In gliadin, we have sulfide groups that form very tight sulfide bonds. We also have covalent bonds. Covalent bonds are some of the strongest bonds that can be formed inside the structure. And so this results in a very aggregate structure. The tertiary structure of gliadin is very compound. Think about a ball or a marble. Now with glutenin, it has sulfide ridges that make it long and stretchy. That movement of stretching and relaxation is what we do when we're kneading the dough. So I'm going to use this here to illustrate how gluten actually works and how kneading works. So we have gluten that exists in this format. Then you start mixing it with ingredients. In the process of mixing it, we're going to introduce ingredients which are going to break down this complex structure into something that is more organized that you can work with. And then once you've mixed it with ingredients, so this is where you mix your sugar, your oil, and then you start kneading. Now when you start kneading, that's when you're taking this and you're forming it into a very complex structure. So now we're going to move on to the practical aspect of this all. If we were to take a microscope and look into the molecular structure of this flour, we will see the very complicated glutenin and gliadin compounds, because that is how they exist at this level. They are not interacting yet. That's why our flour looks like this. I am going to add some salt. So if we zoom into the amino acids that are found in this flour, we'll find some aspects of them are charged. Like charges repel and like charges attract. So the areas that are charged within this molecule, remember we're dealing with glutenin and gliadin, the areas that are charged, they have the same charges, they're going to repel each other. So by adding this sodium chloride, what we do is that we're introducing positive ions from sodium and negative ions from chloride, and these two components are going to find those charged areas in those charged amino acids, and they're going to bind with them. By doing so, those amino acids are not going to repel each other anymore, which means they can now interact. What this sugar does is that it hydrates the flour. By hydrating, I mean that when I finally add water, the sugar is going to form very strong bonds with water first and foremost. So the gluten in the flour is not going to be able to access this water. Once the sugar is bound to the water molecules, it's going to make my final product a lot softer, because you still have those water molecules that were unadulterated during the chemical process. The next thing I'm going to add to this is oil. It bonds with the amino acids that are hydrophobic. Hydrophobic amino acids are amino acids that do not interact with water. By bonding with them, it also makes them accessible to interact with the rest of the glutenin structure. As you can see, my dough has kind of started becoming sticky. That means there's a chemical reaction that's already started. The proteins are starting to interact because of the ingredients that we've added. Now, the very last and probably the most important ingredient in this is water. It contains positively charged hydrogen atoms that are going to interact with negatively charged oxygen or nitrogen atoms within the flour, and they're going to form hydrogen bonds. You can see it starts to stick together. Those are active hydrogen bonds that have now started forming the gluten. Our dough is now actively sticky. This is the part of the process where we finished mixing and now we've started kneading. I am bringing the gliadin and glutenin molecules into close contact so that I can stretch out the glutenin and insert the round molecules of the gliadin. If you want your chapatis to have multiple layers, make sure you just take your time, be patient with it and knead it. You can see right now it's a bit sticky, but if you continue knead it, you're going to notice its texture is going to change and it's going to firm up a bit. My dough is done. In many recipes, you'll notice they tell you to do this, and if it bounces back like that, your dough is done. But why are we doing that? Remember we said gluten has glutenin and gliadin. Glutenin is the one that is long and stringy and acts like a rubber band, and its main function is elasticity and holding shape. If we do this and it bounces right back, like you can see it's reforming to its original shape, that means my dough is fully elastic and it's ready to be used. So one of the crucial steps in making chapati is that step where you form the layers. The layers of the chapatis are very important. Not very important, you can do without them, but they make for a very pleasurable eating experience. I'm going to roll this out, spread some oil on top of it, and fold it into layers. The layer of oil that you're going to add on top of this is going to prevent the gluten layers from combining. Remember we said oil acts on the hydrophobic amino acid, hydrophobic I mean, and by doing so it prevents the reaction or the interaction between adjacent gluten layers, and so it's going to give us some very distinct layers. You can see that there are some bubbles around the edges, like this one. They are trapped carbon dioxide that is going to be released during the cooking process. and make our dough rise. So at this point, I'm just going to make a very rough shape. I'm going to spread my oil. Here we have our dough. I'm just going to spread some flour on top of it and light it. Just douse it with flour so that it doesn't stick on the surface. And then I'm going to start rolling. So one thing my mom taught me is to roll away from the center, because you want to reduce the thickness of the center, because as you roll you'll notice that the dough tends to shrink back. So after a while you can see some pockets of air around the dough and they're growing even bigger. These pockets of air, you remember the water that we added initially? That water is now being heated up. It is being released from the gluten as water vapor, which is filling up these air pockets. We also have carbon dioxide within the structure of the dough, and it's filling up these air pockets. The all-purpose flour that we use, it has about 13% of protein, but up to 70% of the flour is starch. What happens is, as the air is escaping and forming these huge pockets, the starch will expand to occupy this space, which results in a structure that is composed of the gluten itself, the starch molecules, and the carbon dioxide. Forming those pockets is very important during the heating process, and you have to knead your dough enough for you to trap the right amount of air, and your dough has to be well hydrated as well. Some chapatis. I'm using aluminium foil and a kitchen towel to cover them. It's good practice to cover all your gluten-based products because of a process called starch retrogradation. Retrogradation is when chapatis and breads and mandazis are exposed to air and they dry out. The starches start to crystallize and to rearrange, and then they form a much tougher structure. As you can see, the kitchen is a very fun place to be. There's a lot to learn, there's a lot to try out, and it's a very practical experience. So I am just going to enjoy chapati, and I will see you guys on the next video.